Alright, hell yeah. So how big is the Earth? This one's cool. I was over at my brother's house and I was just like, oh yeah, you know how much a degree of Earth is? And I said it's about 60 miles. And we were just like, no way. Or he was like, no way. And I was just like, yeah, we can do this just real fast in my head. So no calculator. Like, and this isn't, so we're going to get to Eratosthenes, you know what I mean, his stick in the ground and the sun, and we're going to do that experiment for ourselves, but not in this video. But anyway, just from what we know, so this is how I know how big the Earth is, because I know what a time zone is. Now in Montana, we're up about 45 degrees, so our time zones are only about 700 to 800 miles apart. But I do know at the equator, time zones are 1,000 miles apart. And I know it's fairly close because up in Montana, I kind of know going from one time zone to another, like I said, about 700 to 800 miles. But on the equator, yeah, for sure. So just in my head, 1,000 miles is a time zone. There's 24 time zones on the Earth, and so we got 24,000 miles. And that's pretty damn close. It's closer to 25,000, but we'll just put that aside for now. And then, so in my head, I told my brother, it's like, we can do this in under a minute. It's 24,000 miles divided by 360. Now, that's a difficult one to do in your head, but it's not, because 24 and 36 are about the same number. So just make them the same, because if you divide those are going to cancel out. So even though 24 divided by 36, you're going to get a little less, you know what I mean? So, but bear with me and keep that in mind. Actually, at the end, I didn't even keep that in mind. I was just like, we got this, because 24,000 turns into 10,000, 10,000, and then the what the hell is this circle? 360. Yeah, 360 turns into 100. So now you're dividing 10,000 by 100. I know that 100 has 2 zeros, so I just want to take 2 zeros off 10,000. That's going to be a tricky one, but it's just 100. You know what I mean? So there you go. The answer is 100. That's the fastest way to just kind of guess that 1 degree is 100 miles. And I think I did it even faster. I did it in about, I'm pretty slow on camera, but I did that in about 20 seconds. You know what I mean? Like, oh, we got this. You know, and 20 seconds later, I was like, yeah, it's pretty close to 100. You know what I mean? Because he had an aha moment. He was just like, no way. Because if you say no way to 60, he would for sure say no way to 100 and miles for a degree. And so that brings up, like, physics, especially first chapter. And they teach it just a very quick little paragraph sometimes in physics books, but it should be drilled in that you always want to have a good guessing skills for factors of 10. So if you think the answer is 100, you know what I mean? Cool. It's not 1,000. It's not 10. But yeah. So that was pretty cool. And then the question was, because I looked up this, you have, and I said, yeah, this is such a fable. You know what I mean? Because the deal is that on the highest noonday down the well in this little town of Syene, no shadow was in the well. And then, however many miles away, it's probably pretty substantial, in Alexandria, you're going to measure a shadow. If you put a stick straight up, you're going to measure a shadow. So kind of the legend story goes is on the highest noonday, where there's no shadow here. But then I asked my brother, it's like, it doesn't matter at all. Like, this story actually is so fable-ish that it doesn't, like, all you need to do is measure those two angles on the same day. I shouldn't be screaming, but you would have to do it at the same hour, but you really don't even have to do it the same hour. You just have to, like, when you put a stick in the sand, it's going to cast a shadow, and maybe that shadow grows and then it retreats. So all you have to do is have someone watch that shadow grow, and then the second it retreats, hell yeah, you got a max. So as long as you get the max shadow length on both days, and if you're stick height then shadow length, hey, you can figure out the angle there because it's a tangent, because you have opposite over adjacent, and now you're in business. But what I was telling my brother is just like, well, it doesn't matter, right? It doesn't matter that it has to be a high noonday, because I was just like, this is such a fable. You don't have to do it on the highest noonday at all. You can just do it you have to do it on the same days, or fairly close. You know what I mean? You'd have to do it one day in a town and then book it using horses. Hopefully you can get about 60 miles away and then measure another shadow. And if you have like a plumb bob, you know, marked with the appropriate lengths, and those lengths are fairly substantial, you should be able to figure out what 1 degree, because 1 degree, let's say you have like 100 millimeters, I think 1 degree is about, you know, 1 or 2 millimeters, so, you know, I mean, if you do your plumb bob pretty high off the ground, and you should be able to measure a 1 degree accuracy, and hopefully just a little bit more, because that's all you're going to get. You're going to be able to, you know, in a day go 60 miles by horse, maybe even less, and try to measure that degree, but you could get fairly accurate. All right, hell yeah. So my question was just like, well, and I just asked my brother just off the spurs, just like, well, does it matter? So that's what we're going to do. That's what I did. And I've just set up the experiment so then I can, and I'm sorry it's just real light, but we can maybe darken it in. I don't really care about this. So what we're going to show, and in this diagram, you know, we have the Earth. And then I'm up here, I guess I'm north, and my brother's in Bozeman. And these are 1 degree apart, just a little bit less. But Helena, Montana to Bozeman, Montana is a 1 degree separation. And so the next time I go visit my brother, you know what I mean, I'll probably just, I'll measure the sun in the sky with a plumb bob, and get a shadow length and just mark the time. Let's say, even if it's 4 p.m., you know, it could be late in the day, and then I'll come back to Helena the next day at 4 p.m. and do that same setup and measure the shadow length. Now, and this is kind of a side, but we were also talking how the Earth definitely has a tilt, but that tilt, you know, and that was kind of fascinating because my brother was like, oh, what is that tilt? You know, and I was like, well, I just kind of, I thought it was 21 degrees, 21, 22. No, it's 23.5, but that's a good one. It's a good one to know. But then as the Earth goes around the sun like this, you know, like here, like because the Earth is tilted, we call this the equator. But actually, you know what I mean? If it's in this, like the equator's down here, where like in this place, hey, somewhere up north is actually getting high noon sun. You know what I mean? The equator will be spinning, and the equator won't even get high noon sun. But then when we're over here, we're still angled like this, and oh, check this out. So now the equator's up high. Somewhere in the south is getting hella high noon sun. You know what I mean? So, and then, but no, my brother was right. Because he's like, well, isn't the tilt of the Earth 45 degrees? And I was just like, I chuckled. I was just like, that's the dumbest thing I've ever heard. But no, 23.5 plus 23.5, hell yeah, it's going to be pretty close to, you know, 45 to 50 degrees. So if you add these up, this is the oscillation of the sun. And it was just interesting on the internet. I couldn't find this. Now it's not going to be linear. But in the course of 365 days, you know, if we put this on this axis, we are going to see a change in this high noon. The change in the angle the sun is in. Like, let's say you are up here. Let's say you're at the equator. You know, the sun's going to be hella over there. You know what I mean? Let's say, you know, to the left, or I don't know. I don't know my I'm pretty spatially bad. But then when we're over here, hell yeah, the sun is. You know, if we're at the equator over here, the sun's over there. You know, so over here, the sun's over there. Over here, the sun's over there. You know what I mean? So the sun, at the highest part in the sky, let's say it was over here, and then we're on the equator, so hell yeah. During the summer months, it's going to be directly overhead. No. I have that wrong. No, during fall and, oh, my bad. No, I looked this up. And, see, I'm even making a mistake. So during fall and spring, the equator will be right in line with the sun. You know what I mean? Because you'll just be, how does this work? Oh, yeah, yeah. The tilt will be sideways, but it doesn't matter because the equator will fall right in line with the sun, here and there. It doesn't matter that this tilt always has to be the same, but it's going around. But anyway, so you have fall and spring are where that's going to be right there. And then it's going to dip down, and then it's going to come back, and then it's going to dip up, dip down, center, down, center, up. And so on this axis, we're going to be, I mean, we could do it like this. We're either going to be we're going to have 4 seasons. So, booyah. And here's where it's going to be in the summer. Now, if I'm at the equator in our winter up north, the equator must be, like, down. You know what I mean? Because we're getting all the sun up north. So, hell yeah. So, this is going to be winter, spring, summer, fall. But this is fall. So, hell yeah. And then, yeah, we got this. And so, the tilt is going to be down here. So, we're going to go down here to down there. And it is probably going to look like this. The greatest change in the slope will be at summer. Hopefully I got, yeah, does that make sense? I thought this graph was going to be the other way around. I'm glad I graphed this out because I thought the biggest change was going to be in the winter and, oh, no, spring. That's when I thought the biggest change was going to be in the spring and the fall, and that's what we see. Alright, hell yeah. So we already finished the video, but I'm going to interject right here. So what I was trying to figure out is if like spring and fall is just not the time to do this test. And so how do you take this is what I'm going to show you. How do you take a graph like this and kind of tweak it, you know? So what I like to do, and this is what I do with circles because yeah, let's show this, because if you have a sine of x, and then you're going to have 30, 60, 90. You want to divvy this up into 3, and then hey, this is just going to be 1. You know what I mean? And then and then it's gonna do something like this, go up, and then it's going to go down, and then it's just going to go sinusoidal. But when we have something like this, we have like a slope of 1. And then I like to take this, I like to guesstimate, because at 60 degrees, it's going to be like 0.866, you know what I mean? At 30, it's 0.5. But I just say, hey, instead of 0.866, sometimes you can just really guess that sine of 60 is 1. So this is what we're going to do. We're going to take this all the way up to there, and then we're going to flatten it out. So we're going to come here and do that same thing. So if this is... 1, 2, 3, 1, 1, 2, 3. And then we're just going to flatten this out, and then we're just going to take this. So now this is what our graph looks like. And so, and then we'll do that same thing down here. So we're going to flatten it out here, and then 1, 2, and then so we're going all the way through here. Okay, so now we can kind of get an average of like how much degree change is going to happen in one day. And so, man, I kind of made this messy. But each of these is a season. So this is fall, winter, spring, summer. You know what I mean? And then we're kind of done. So one of these things is 3 months. That's right. So cool. So one of these things is 1 month. So this actually works out really well. And this is 23.5 degrees, and we only need to do one. So in 2 months, we're going to go from 0 degrees to 23.5. It'd be the same thing as going 4 months and then doing that, adding those up. But hell yeah. So now we have 23.5 degrees in 2 months. That's 60 days. And so this is going to be the degree change. And you can just see that it's going to be about 0.5 degrees. So, hell yeah, just from a very rough estimate, if we're on one of the worst days, you could expect a 0.5 degree change. So, if I measure in Helena if I measure in Bozeman one day, and then one day later go to Helena and measure, my error could be up to a half a degree off, you know what I mean? And I don't even need to do this 23 divided by 6. We could do 23.5 divided by 60. It's 0.4, you know, so you have 0.4 degrees. But again, this was just a really rough estimate. You know, this might be a little bit steeper. Like if you are on the equinox right at spring or fall, you know, it'd be the worst time to measure. You know, you wouldn't want to measure the shadow one day, drive to another town the next day up north or south, you know, depending on whether what hemisphere you live in. And then yeah, because if you're only going to measure like a 1 degree change, that's going to be difficult in itself. And if you know your accuracy is going to be plus or minus 4 degrees, that's really going to mess up your calculation. So hell yeah, that's just another reason to do this in spring and summer. All right, hell yeah. So let's get back to the video. In the fall and spring, so that's the only thing that makes sense about the legend is from this analysis. You want to do this test if you're going to do it at 2 different days. You know what I mean? If you're going to measure this one day and then travel by horse north to a different town as far as you can, and then the next day try to get the highest point in the sky, you know what I mean, and measure that angle, hell yeah, you want to do it during the winter or the summer. And obviously the summer, if well, it doesn't matter if you're close to the equator. It really doesn't. But during the summer and winter are good times to do that, because the change in the highest point. So if we say, hey, today the highest point, the sun got up to here, but tomorrow the sun only got up to here. That's going to change our angle. And this change will be greatest in the spring and fall, but that change will be pretty much the same in the summer and winter. So I think we got that covered. Hell yeah. And we need to get to the analytical part of this, which is fairly interesting. So what I'm going to say is that, hey, there could be an angle here and then just a bigger angle there. So let's take a look at that. So what I have here is I measured my stick to be 26. So this length, this is going to be my stick. It's 26 millimeters, and I'm in Bozeman. Cool. And I guess I'll just put Bozeman and Helena. Now, I used graph paper because I didn't want to draw in all the lines going this way. You know what I mean? I drew in one, and this is the sun ray going that way. So booyah. And so all these graph lines going this way are the sun's rays. Okay, so now let's go to Helena. We're going to do, and you want to do this with a plumb bob, and then a string, and then mark the length of the string, put a little, you know, a nugget right there, and then you can actually see the shadow of that nugget or whatever. Anyway, so, oh, and that's not even it. So if the sun's rays coming in and hitting this stick, hell yeah, look at that. So you can obviously see that this distance here in Helena of the shadow is going to be larger than this distance in Bozeman. And again, who cares what time of day this is? You know what I mean? This could just be 4 p.m. sun. You know what I mean? So that's kind of what we, hopefully it's close to high noon. You know what I mean? I didn't mean to say 4 p.m. is a good thing. All right, but booyah. So now, like right here, it's just really easy to see. Someone was saying, hey, do complementary angles. Well, this is numero uno. The first thing you need to learn in trigonometry is like, hell yeah, if you do have an angle, and I know it, but then I have another parallel line that's parallel to one of these, you know, faces, then hell yeah, I know the other angle. And same thing here. Look at this line. So if I have this line, and then I just draw a line parallel, that's not a very good job. Then, what is this? Oh, to this one. So here's the angle, and then I zero over here. So hell yeah. So this angle right here is the same as that angle. All right. But when we do the experiment like this, we get 2 different angles. And so I just hypothesized that, well, the difference between these angles has to be this. You know what I mean? And I'm going to call this theta star. So this is angle 1, angle 2, and And let me go over how to get these angles. So if this is angle 1, angle 2, what we do know is that this height of our stick is 26 millimeters. And then we can just measure the shadow length, which we did here, and we got, oh sorry, I'm going to cross that. I don't even know what that was. Oh, this was, yeah, we'll get to that in a second. But our shadow length for this one was 6.6. Actually, we're going to call it 7. I kind of redid it. 7 millimeters. And so, you know, the first attempt was 6.6, but I redid it. I redid it with 7 millimeters. I shouldn't have crossed that out, but anyway, you get this length, and you know this length, and you know, and you're trying to find this angle. Well, tangent says if we know, like basically you say tangent of this angle is opposite over and I would write that opposite over adjacent. Sorry. And how do you find the angle? Well, you have to get this tangent part over there. We do that by using the inverse tangent. And thank God our calculators just do this for us. And so that's what I have. And you can do this all in one go. You're like, hey, I want to know that angle. Angle 1. What do I know about this? Do I know the hypotenuse? No. But I knew opposite over adjacent. I'm thinking tangent. So I'm going to say this angle is inverse tangent. And then just do them in order, opposite over adjacent. So it's going to be that 6.6 divided by 26. And that's what we get here. I should just do the first attempt. So we got 14.24 degrees. Over here we have a height of 17 millimeters. Stick is 26. So we got inverse tangent of 17 divided by 26. And then we get 33.18. Just take the difference between there. In my first go, I got 18. It was just a little bit big. And then I doubted myself of if this even works, you know, taking the difference between these. Is the difference between these this angle? That is what I did not know, you know what I mean? But, so we're going to end this video trying to prove it. I think I do a pretty decent job, but I don't know if it's like 100% proofy. Alright, and I threw in some different values. Like I said, I threw in 7 for this one. I don't know if I changed the other one. I just changed this one up a little bit. We went to 15 instead of 17. And then I got a change in angle of 14.9. I measured this to be like 14, and my actual angle should have been like 13.7. But hell, that ain't bad for just, you know, doing this in a very small circle. I mean, figuring out the dimensions of this circle using like little sticks, and you know, you can just imagine that if you have a big earth, you can get pretty damn accurate. Like the bigger the circle, the more accurate you're gonna get. Okay, hell yeah. So now we're gonna finish this video by trying to prove that the difference between these two angles is this representative slice. But we should figure out, what the hell did we even do with this angle? And let's say we are using this 14.9. So we know that if our representative slice is 14.9 degrees, we know that there's 360 degrees in the circle. We're going to divide by that 14.9 degrees. And this gives us a multiplication factor, 360 divided by 14. Alright, hell yeah, sorry about that. Camera ran out of juice, but yeah. So when we divide these, we get we're going to multiply by 24. What are we going to multiply by 24? Well, this distance. We kind of found this arc length, and we didn't even find the arc length of the curve. We're just kind of straight up saying that this is a right triangle. You know what I mean? And we're just going to measure this, and then right triangle measure this, get this angle. We know the radius of oh damn it. Oh no, we're good. That just caught me off guard. But yeah, this part, we don't know the radius. If we knew the radius of our Earth, hell yeah, we'd just be in business. But we just know this is going to be like 14 millimeters because we paced it out. You know what I mean? We that's the thing. We traveled from Bozeman to Helena. We know this distance. For our problem, this is 14 millimeters. So we're going to take that 14 millimeters times that number, and we're going to get 338 millimeters for the circumference of the circle, but we do know the radius is 50. I did measure it, so we're going to go 50 times 2 pi. You know what I mean? If the diameter is 100, that's 100 pi, right? Because circumference is pi times diameter. It's also 2 pi times the radius. That's what we're going to do, 52 pi r. Just 50 times 2 pi, and you get 314. So this was just an overestimate. That's why I was trying to figure out. I went back and be like, well, did I over measure just a little bit? So sweet. So that's how you actually get, and I'm sorry I didn't spend too much time on but I think, no, that makes sense. You're trying to find the angle. 2 sticks in the ground, you have a change in angle. That difference between the angle is the representative slice of those 2 locations that you walked off. So let's say that representative slice was just 5 degrees. Cool, you're going to take 360 divided by 5. There's going to be 72 of these distances in the circle. If you walked it off and said it was 50 feet, what are we doing? Just if you have this circle, like you could do a basketball, you know what I mean? And let's say you got 5 degrees of a basketball, and you thought one of the inches, like I don't even know, you know what I mean? Because this is 14 degrees, so 5 degrees is going to be tiny. And I don't even know what I'm saying, but anyway, if you did, what do you think a basketball is? How many, it's about a foot across, so you got like 3 feet, not quite 36 inches in circumference, so maybe the circumference is like 28 inches, and, you know what I mean, so maybe a 1/4 inch, you know what I mean, so times 0.25, and, so you would you do little 2 sticks on a basketball, and maybe the difference between those angles is going to be about 5 degrees. And you're going to do 72. Maybe it's just those are ½ inch apart. I'm just kind of giving an example. But now, anyway, we got to move on to actually kind of proving why the difference between these angles works. And you could do it basically at any time of day, just as long as the sun is in the same location. And again, if you're going to do it at 2 different days, the angle of the highest point in the sun is going to change. Or the angle at the same, like if this is 2 o'clock one day, the sun is going to be at a different height in the sky at 2 o'clock the other day. You know what I mean? And hopefully it's just in a different location over here that doesn't really change the effect of the shadow. You know what I mean? Maybe it just is just in a different location that direction and not so much height. And that brings up another good point, is like if the sun rises, and because if you do live like kind of in a like I live at 45 degrees, and literally the sun in the wintertime pops up over here, goes across the sky over here, and then lands over here, and I'm literally right here. Like I look at the sun over there all day long, and it never goes above my head. So I guess what I'm pointing out here is for this observation, hell yeah, like at let's say even in the wintertime at about 1 p.m., like maybe the sun is right there, and then at 1 p.m. the next day, I don't know, maybe if we're approaching winter, so maybe it's this way and just down a little bit. But that's going to be a lot better than if I did this experiment right at this point, and then it's going to be over here, because over here drops it. See how it dropped? So it's over here and down a little bit. So you definitely want to do this experiment at the highest point in the sun, and you could set up you could set up a ruler and a camera, and just make sure when you got your stick, you are actually getting the highest shadow, and then the sun kind of goes back down, and then you're going to mark that highest location. Or, who cares, and then just 2 p.m. in Bozeman, do this experiment, and go to Helena, and then just that same time at 2 p.m. I think you're going to be able to do this experiment fairly accurate. So I'm kind of looking forward to doing it, and with the last moments, let's, and we got chicken scratches now, but let's try to prove why the difference between these angles is that representative slice. Alright, so this might be kind of hard. I don't even know what I did. Yeah, this was interesting. Alright, yeah, this was not easy. I had to play around with this a long time, but alright, so we do have this, this is my stick. So this is the center of the earth. This is your plumb bob. The plumb bob always has to be the stick going towards the center. Because of gravity, that's going to be making that stick perpendicular, vertical with the earth. Okay, so what I did is I took this line and then came up to this point on this stick and then drew in a parallel line. Okay, sweet. And then I saw that this line is also parallel with this line. And so, like, I don't know what proof this is, but it's a decent one. Because, if these two lines are the same, and I have an angle here that's theta 1, and then I go up and put my baseline right here, okay, and then so we're basically checking out this angle. And then I have, this is the top of theta 1, and it's also parallel with this, then this has to be theta 1. So let's go over that one more time. I'm coming in here, and I'm making this line. And so these two lines are parallel. I know for sure this is theta 1. And then I come in here, and I know that this line is parallel with that. So this has to be theta 1. And then this whole thing is theta 2. So this representative slice right there, 1, 2, 3, I'll just do that because booyah. And then we come down to here, this slice. This is the Zorro slice. So we have this Zorro slice. This is 1, 2, 3. So this is our representative slice. I'm calling it just theta star. And hell yeah, a little bit sloppy, but we did it. And this video is definitely under an hour. So this was pretty sweet. And it's just fascinating that some of these stories, what I'm going to point out the most is the legend aspect of these stories make them seem like you can't just repeat them. Like I could use this light right here that I'm using and a basketball or a beach ball, and then just stick some sticks to it and then try to get them to be fairly vertical and then, measure the angle. Just really rough, and I could probably estimate the circumference of a basketball just using a light. So yeah, it's just kind of fascinating that this experiment, I'm just going to call it out. The fact that they're like, oh yeah, high noon on the highest day of the year, down a well, it was perfectly vertical. It makes it seem like that's necessary to do this experiment, and so I'm just kind of debunking that. But kudos to this guy because no one knows who he is. His name's really hard to say. He should have had a simpler name, But Eratosthenes. I don't know if you say Eratosthenes or Eratosthenes. It's really difficult. Eratosthenes. Alright, hell yeah. Give it up for that guy. Sticking sticks in the sand. And we just found out how big the Earth was. Oh, you know what I mean? We gotta end it with some coolness because hell yeah. So what is the actual so the actual dimensions of the Earth is like 24,900 and maybe like 2 or something. And then we're going to divvy that up between 360 degrees. So we got 24,902 divided by 360. And hell yeah, we get 69.17 degrees. And I think it's actually just 1. So 24,901 divided by 360. Yep, that looks more familiar. And hell yeah. And so booyah. This is, and then, it's 69, no, it's not, this is degrees, so this is miles. So every degree is going to be 69 miles. So there you go. And I'm bringing sex into it because that's how you can remember some of these things. You're just like, oh, hell yeah, 1 degree is 69 miles. You know what I mean? I can totally remember that. And it's a palindrome at 69.169. You know what I mean? or it's just 69 point and it takes 2 people. You know what I mean? So there you go. So that's a freebie on me, because now you don't even have to know 24,000 miles anymore. You have this other way to know the circumference, because now you can just say, hey, this representative slice is 69 times 2 people, and then times 360 degrees, because this is, what is the factor label on this? This is miles per degree times 360 degrees in a circle. So 69.2 times 360. This will get you, because I don't even know the actual circumference, you know, to any accuracy. You know, I'm not going to be able to memorize that. I'm going to lose this. 24,901. I'm for sure just going to know the circumference is 24,000 miles. We went over that. Equator, about 1,000 miles per time zone. That's a very easy one to memorize. But hell yeah. So this gets me pretty close. 24,912 miles, and I'm not too far off. So, you know what I mean? And if I just did 69 times 360, you know, we're in the ballpark. 69 times 360, that's hella more accurate than just saying 24,000 miles. But, yeah, it's just fat. And if you do the palindrome, 69 and then palindrome, so you got 69.169 times 360 is just 24,901. You know what I mean? So there you go. So if you can remember this palindrome, and I probably will for about a month, but hell yeah, it's just kind of cool. That's the other aspect of doing math and physics. It's just kind of fun to make up little things where you can kind of memorize some of these numbers. Now, some of these memorization schemes, they'll only last a couple months, but there you go. All right, how big the Earth is, how big the circumference is, and kind of some ways to dial it in. Alright, hell yeah. Thanks for joining me on this one, and that's the video.